What I want to talk to you about is some work that we've done where we've built a database which actually builds in a lot of things we've heard earlier this morning. And it sort of sounds as if we're converging. So our objective was to build a data set for the development and evaluation of machine learning tools to predict the risk of HIE in the delivery room. And to start with, we wanted the database to include both CTG records and extensive clinical data about the mother, the fetus, and the progress of labor. And basically it was designed to support 2 research grants, one from the Gates Foundation with a focus on deep learning, and one from NIH on a focus of sort of classical machine learning, although in fact the 2 cross over a lot. I mean, it's a situation where they're synergistic. Now our target population were singleton births from 15 Kaiser Permanente Northern California hospitals. Kaiser Permanente is an HMO, a private company that runs these hospitals. We wanted the pregnancies offset in a 10-year period, gestational age greater than 35 weeks, and EFM records and electronic fetal monitoring records. Our data set structure was set up basically with 4 components. A component which we called early, which is essentially all of the clinical information. CTG, which is information about the EFM records and whatnot. Patterns, which essentially is a result of running Perigen's pattern software, which generates information about the patterns in the CTG signals, and then the EFM files themselves, which were stored on disk. A little bit of information about each of them. So the clinical information was the mother, the infant, the pregnancy, and the intrapartum. We defined 2 types of information: static, that is information which is available at the start of labor, and dynamic information, which essentially is time-varying measures throughout intrapartum, including fever and questions about disease, right? And we also have some derived measures. And then we also have the trace ID, which links the actual clinical data to the CTG record. And in fact, all of the protected health information is removed. So for the people who worked on this, all the data is untraceable to the actual subject. The CTG component basically points to the location of the CTG file, has information about what's in the file, the processing status, and then epoch-based features. So basically what we've done is we've analyzed the features for 20 or 30-minute epochs throughout the recording. Patterns component basically points to the CTG tracing after it's been repaired. Clinically relevant FHR and UP patterns are identified, and then summaries of these patterns over each epoch. And the EFM files themselves include the raw files, files that have been combined, I'll talk about this in a minute, repaired tracings, FHR, UP, and maternal heart rate, up to 72 hours before birth, and these stored in a custom format which makes it easy for us to acquire the data. Now, building early, one of the advantages of having a HMO is supposedly all the hospitals use the same systems. I say supposedly. We heard earlier some of the problems associated with acquiring data from different hospitals. But basically our clinical people and KP people drew data from a whole series of internal databases, including the electronic health record, and essentially built the early data. So essentially what we have is for each mother and for each infant, we have a whole variety of records. I don't think I've actually counted them, but it's clearly in the order of hundreds. And if we take into fact hourly records, it becomes large. Early also includes outcome from each infant. So we have an objective outcome in the database for each infant, and all of the HA cases were confirmed by a clinical review of the patterns. In fact, Yvonne Wu, who's here in the audience, and her colleagues basically went through some 1,000 clinical files to confirm the output. And essentially we defined each patient as being HIE, someone who had acidosis with no HAE, healthy with no acidosis, and in fact the majority of instances were healthy with no blood gas, so we couldn't actually confirm they had no acidosis. And there were 2 or 3 other sort of smaller situations. The block diagram on the right, which I'm sure you can all read and understand, basically is the formal way that we went through and do this. So basically what we can get is from the information which is the early database, we can derive the outcome. The other thing we did, which I think addresses one of the questions that we raised earlier, is each cesarean outcome is assigned a priority. So urgent being something which is an emergency C-section, a clinical decision, an indication for C-section, and then a planned C-section. We thought it was important to understand what the outcomes were. Why was the C-section done? Was it done because the clinician identified a problem, or was it simply because the mother had had a previous C-section, or perhaps some other reason? The flow diagram on the right shows the flow diagram we used for identifying the patients who had an emergency C-section. There's a whole additional flow graph which is not shown, which shows the other. Now, this is the processing scheme that we use to handle the CTG signals, and each box contains a whole set of subsections. The first thing we did was we retrieved the files and de-identified them. Sounds simple, obtaining 15 files from a bunch of servers, including one of the servers included CDs in the desk of one of the obstetricians. So we basically retrieved them. There's a pre-processing situation in which we did essentially linked the CTG files, which were originally linked to the mother. We linked them to the infant, got rid of garbage, sorted them whatnot, and then it went into a system from Paragen, which repairs it. Essentially what this does is it gets rid of dropouts, and if there are holes which are less than 15 seconds, it interpolates, and then it also gives us a measure of what the quality of the CTG signal is. And basically at each stage, we can see that the data from each stage is actually stored. So we have the raw, we have the pre-processed, and we have the repaired data. After it's prepared, it goes through the clinical pattern identification, in which the Paragen software identifies at each sample, whether or not it's in a particular pattern or not. And then the pattern information is stored in the patterns database. It then goes on to feature estimation, where we divide each CTG signal into epochs and estimate a whole series of FHR and other features, both on the epoch-based and within each epoch according to each pattern. So we have FHR features for the whole epoch and FHR features for a particular pattern. That information is stored in the CTG schema. A few details about the CTG. If we looked at the original CTG section, we can see 2 things. We can see, first of all, you don't have a continuous signal. There are gaps. And the other situation we can see is it's not unusual to have fetal ECG and heart rate either from an external or from the TOCO early on. So we've got ECG from 2 signals. We have UP from 2 signals. So the first stage of processing is what we did is we essentially combined these, essentially picking the sensor which we thought was the highest reliability. We can see in the FHR signals, you can see these dropouts. These are short periods in which we've lost signal. So when they're repaired, what happens is the repair goes through, gets rid of the dropouts, interpolates signals, and then aligns the repaired FHR with the aligned UA. Then the clinical patterns which are identified, I don't think I need to go through these. These are the standard clinical patterns that the obstetricians look at. And then for each pattern, we identify its onset, its end, and a set of sequence. So here's an example where we've essentially identified the patterns in the FHR on the top and the uterine activity in the bottle. You can see we've identified baseline in blue, decelerations in pink, and accelerations in green. And in the UP, we essentially identified the contractions. This is all done automatically by the Paragen software. And then essentially for each pattern we've identified, there's a set of parameters identified. So for each pattern, we know its onset, its length, its height, and other variables. And then essentially for epochs, we essentially summarize what the patterns were and what the statistics were. And essentially what we've gone through is we've identified these features for 10-minute, 20-minute, and 30-minute epochs, so we can essentially track the time-varying behavior of this behavior. The other thing that we've done is essentially by combining the clinical data with the contraction data, we're able to actually identify when labor onset occurs. And what we show here on the right hand is essentially the cumulative distribution of labor lengths, where the blue is healthy, green is acidosis, and red are HIE cases. And as you can see quite convincingly, one of the things you notice about the pathological cases is the labors last longer. And so if you're actually analyzing data as a function of time before birth, this may be a complication that you need to commit. So we think it's important to be able to essentially identify when labor started and use that as a landmark. What's actually in the database? Well, the three things that we focused on are healthy with no acidosis, acidosis with no HIE, and HIE. As we go from left to right, we have the number of births that there were, the number of files that were provided to us, the number of EFM files we came from these files, because some of these files, interesting enough, had no data in it, and then the repaired files. And the bottom line is we're getting data from about 80% of the births over this 10-year period. We can see the healthy no blood gas is the majority of the signals, some 177,000, and then the other ones are somewhat smaller. The patient data itself, sort of the maternal age, median age is 31 years. Minimum is 12, maximum was 56, in which I basically asked the question that I think one of the previous authors said, are these actual real data? I was assured from my clinicians that it was, but again, the real question was. And then we have pH, base deficit, APGARs, gestational age, and neonatal weights. This simply gives us a measure of the CTG coverage as a function of time before birth. So this is the percentage of potential subjects for whom we have CTG records as a function of time before birth. And as you see, as we start off low, and we come close to 80% at the end. And so essentially what we have is we have good coverage. And in this case, what you notice is I've screwed you up by using a different color code, but the HIE subjects actually end up having better coverage than the other subjects, suggesting perhaps that in these cases the clinicians thought something funny was going on. What are the key aspects? First of all, it's the size. It's 250,000 births from a fairly consistent situation. Most of the KP hospitals use the same setups that have very fancy electronic health records and whatnot. Extensive clinical data. Objective outcome definition. So we're quite confident that we know what each patient becomes. The fact that we've identified the clinical patterns. Also that we have CTGs up to 72 hours before birth. In some cases, it's terrifying exactly how long these poor ladies were in labor. And the other point is that we've essentially measured FHR and UP features both as a function of epoch and as a function of patterns, so that we can tell you what the FHR feature was for each pattern as a function of epoch, as well as the overall. And the final component is the actual fact that we've measured or developed objective ways of determining labor onset and the priority for C-section. Here's just a picture of the team. It's an interesting collaboration. I think it's what I tell people true biomedical engineering should be. Basically, it's a collaboration between the Department of Biomedical Engineering at McGill, Paragen, which essentially develops interpartum software, and people from UCSF and from Kaiser Permanente. And it's been amazing to me just how well everyone has worked collegially and what we've managed to achieve. Funding, as I say, has been from the Gates Foundation and from the NIH, and thank you very much.